Hello and welcome to our journey into the fascinating world of artificial intelligence, machine learning, and deep learning. I'm thrilled to have you join me as we unravel the technologies shaping our future. You've heard the buzzwords AI, ML, DL, but what do they really mean, and how do they connect? Think of it this way. AI is the big umbrella, the broad concept of machines performing tasks that typically require human intelligence. Within AI, we find machine learning, which is AI that learns from data without explicit programming. And nestled inside ML, we have deep learning, a powerful subset using complex neural networks. For centuries, humans dreamed of intelligent machines. From ancient automata to sci-fi robots, the idea persisted. But it's only in recent decades, driven by massive amounts of data, incredible computational power, and sophisticated algorithms, that AI has truly taken off. We're now seeing AI transform industries from healthcare to finance, entertainment to transportation. So why is AI such a transformative technology today? It's about its ability to find patterns in vast datasets, automate complex processes, make highly accurate predictions, and even create entirely new content, which we'll explore in depth with generative AI. This course will demystify these concepts, guide you through their practical applications, and equip you with the knowledge to understand and even build your own intelligent systems. Let's start by looking closer at the different types of machine learning. Machine learning isn't a single technique. It's a diverse field with various approaches, each suited for different problems. We primarily categorize ML into three main types: supervised learning, unsupervised learning, and reinforcement learning. First up, supervised learning. Imagine teaching a child to recognize a cat. You show them pictures of cats and say cat, and pictures of dogs and say not a cat. You're providing both the input, the image, and the correct output, the label. Supervised learning works similarly. We train models on labeled data, input-output pairs. The goal is for the model to learn a mapping from input to output so it can predict the output for new, unseen inputs. Common tasks include classification, predicting a category like spam or not spam, and regression, predicting a continuous value like house prices. Next, unsupervised learning. Here, the data doesn't come with labels. It's like giving the child a pile of mixed animal pictures and asking them to group similar ones together without telling them what a cat or dog is. The model's job is to find inherent patterns, structures, or relationships within the data itself. A primary task is clustering, where data points are grouped based on similarity. Another is dimensionality reduction, simplifying complex data while retaining important information. It's often used for exploratory data analysis or identifying hidden trends. Finally, reinforcement learning. This is perhaps the most intriguing, inspired by how humans and animals learn. Imagine a dog learning tricks. You give a command, the dog tries something, and if it performs correctly, it gets a treat, a reward. If not, no treat, a penalty. The dog learns through trial and error, optimizing its actions to maximize rewards over time. In RL, an agent interacts with an environment, taking actions and receiving rewards or penalties based on its state. This is the basis for AI in complex games, robotics, and autonomous systems. Each type has its strengths and best use cases. Understanding these fundamental distinctions is crucial as we move into the practical aspects of building ML systems. Next, we'll look at the typical workflow involved in any machine learning project. The ML workflow. Developing a machine learning solution isn't just about picking an algorithm. It's a structured process. Think of it as a pipeline or a life cycle. Understanding this ML workflow is vital for any successful project. Let's break it down into key stages. It all begins with problem definition and data collection. What problem are we trying to solve? Is it predicting customer churn, identifying defects, or something else? Once the problem is clear, we gather the relevant data. This could be from databases, APIs, web scraping, or even sensors. Next comes data preprocessing and exploration. Raw data is rarely perfect. It's messy, incomplete, and often contains errors. We need to clean it, handle missing values, transform it, and explore its characteristics to understand relationships and identify potential issues. This stage often takes the most time. Feature engineering is a crucial, often artistic step. This is where we create new, more informative variables, features, from existing ones. For example, from a date column, we might derive day of week, month, or is holiday. Well-engineered features can significantly boost model performance. Now, the exciting part, model selection and training. Based on our problem and data, we choose an appropriate ML algorithm, perhaps a decision tree, a linear regression model, or a neural network. We then feed our pre-processed data into the model to train it, allowing it to learn patterns and relationships. This involves splitting our data into training and validation sets. Model evaluation and tuning follows. After training, we evaluate how well our model performs on unseen data, using appropriate metrics. If performance isn't optimal, we fine-tune the model's parameters or hyperparameters, or even go back to earlier steps to refine features or collect more data. It's an iterative process. Finally, if our model meets performance criteria, we move to deployment and monitoring. This means integrating the model into a live system where it can make real-time predictions or decisions. And the job doesn't end there. We continuously monitor its performance in the real world, as data distributions can change over time, leading to model drift. This cyclical process ensures our AI solutions remain effective. As we just discussed, data is the fuel for machine learning. But raw data is rarely ready to be fed into a model. This lecture focuses on two critical stages: data preprocessing and feature engineering, which often take the lion's share of project time. Data preprocessing is all about cleaning and preparing your data. One common issue is missing values. What do you do if a customer's age is missing? You might remove the row, fill it with the average age, or use more sophisticated imputation techniques. Each approach has trade-offs. Another crucial aspect is handling outliers. These are data points that significantly deviate from others. While sometimes genuine, they can skew your model. Identifying and deciding whether to remove or transform them is important. We also need to deal with inconsistent data formats or duplicates. Many ML algorithms work best with numerical data, so we often need to convert categorical data like red, green, blue, or male, female into a numerical format. Techniques include one-hot encoding, creating new binary columns for each category, or label encoding, assigning a unique number to each category. Feature scaling is also vital. Imagine one feature, income, ranging from thousands to millions, and another, age, ranging from 0 to 100. Models sensitive to feature scales, like those using gradient descent, can be heavily biased towards income. Scaling techniques like min-max normalization or standardization bring all features to a similar scale, improving model performance and stability. Now let's talk about feature engineering. This is where creativity meets data science. It's the process of transforming raw data into features that better represent the underlying problem to the predictive models. This often requires domain knowledge. For example, if you have date and time columns, you might extract hour of day, day of week, month, or is weekend as new features. For text data, you might create features like word count, average word length, or the presence of specific keywords. Combining existing features, like multiplying length and width to get area, can also be powerful. The quality of your data and your engineered features often have a greater impact on model performance than the choice of algorithm itself. Mastering these techniques is fundamental to building robust and accurate ML systems. Next, we'll explore how to measure and improve our model's performance. You've built your model, trained it on data, but how do you know if it's actually good? This is where model evaluation comes in. It's about objectively assessing your model's performance. And hand in hand with evaluation is understanding overfitting and underfitting, two common pitfalls. First, let's emphasize why we need separate datasets. We typically split our data into a training set to teach the model, a validation set to tune hyperparameters and select the best model during development, and a test set, a completely unseen dataset used only once at the very end to give an unbiased estimate of the model's performance in the real world. Now for metrics. For classification tasks predicting categories, we use metrics like accuracy, correct predictions out of total, precision of what was predicted positive, how many were actually positive, recall of all actual positives, how many were predicted positive, and F1 score, a balance between precision and recall. The confusion matrix is a powerful visual tool for understanding these metrics. For regression tasks predicting continuous values, common metrics include mean absolute error, MAE, mean squared error, MSE, and root mean squared error, RMSE. These quantify the average magnitude of errors between predicted and actual values. Lower values are better for these metrics. Now, let's tackle overfitting and underfitting. Underfitting occurs when your model is too simple to capture the underlying patterns in the data. It performs poorly on both training and test data. Think of it as a student who didn't study enough. Solutions include using a more complex model, adding more features, or reducing regularization. Overfitting is the opposite and often more insidious. It happens when your model learns the training data too well, including the noise and specific quirks, but fails to generalize to new, unseen data. It's like a student who memorized the textbook but can't solve a new problem. The model performs great on training data, but poorly on test data. Solutions include more data, simpler models, regularization, penalizing complexity, or techniques like cross-validation. Balancing bias from underfitting and variance from overfitting is key to building models that perform well in the real world. By understanding these concepts and using appropriate evaluation metrics, you can confidently assess and improve your ML models. Next, we'll look at some foundational ML case studies. Theory is essential, but seeing machine learning in action truly solidifies understanding. In this lecture, we'll explore 5 foundational case studies where basic ML techniques have delivered significant real-world results. Case Study 1, Spam Detection, a classic classification problem. Email providers use ML models to classify incoming emails as spam or not spam. Features might include sender's reputation, suspicious keywords, or attachment types. A supervised learning model, like naive Bayes or support vector machines, is trained on millions of labeled emails to accurately filter unwanted messages. Case Study 2, House Price Prediction, a prime example of regression. Real estate platforms use ML to estimate property values based on features like square footage, number of bedrooms, location, amenities, and recent sales data. Linear regression, decision trees, or even simple neural networks can be used to predict a continuous price value. Case Study 3, Customer Churn Prediction. Businesses want to identify customers at risk of leaving. Using historical customer data, activity levels, support interactions, subscription details, a classification model, like logistic regression or random forest, can predict the likelihood of churn, allowing companies to intervene proactively with retention strategies. Case Study 4, Credit Card Fraud Detection, another critical classification task. Banks analyze transaction patterns in real time. Anomaly detection algorithms, often based on unsupervised learning, clustering unusual behavior, or supervised learning, classifying fraudulent versus legitimate transactions, flag suspicious activities, preventing financial losses. Case Study 5. Recommendation systems. Think Netflix suggesting movies or Amazon recommending products. These systems leverage both collaborative filtering, people who liked X also liked Y, and content-based filtering, recommending items similar to those you've liked before. While advanced systems use deep learning, foundational approaches often rely on clustering or matrix factorization to group users or items and suggest relevant content. These examples demonstrate how diverse and impactful machine learning can be, even with foundational techniques. They solve real business problems, enhance user experiences, and drive value. With these basics under our belt, we're ready to dive deeper into the powerful world of deep learning and neural networks in our next module.